I heard a rumor from the teacher, he might let you use the homework on the quiz too, so. It's up to you. Okay? So, again, I'm gonna try to get through this material and have you work on these problems, from which I'll take, like I said, 3 or 4 questions for you to take a quiz on tomorrow. And then really, if we kind of just look at how the year is gonna finish before we get started, just so you know what to do. We're going to get through some basic stuff on acid-base chemistry. We're going to review something we did first semester. So you may or may not remember doing a titration earlier in the year, where we had the burettes. But we have to go through that again, because that's definitely on the final. We're going to talk about the pH scale. And then we're going to have one more lab that we actually have to turn in. And then other than that, you can see the last week before finals, we'll finish that lab. We'll do a couple days of final exam review, which I will tell you more about the final, but for the most part, if you want to start looking back, the final is focused on 2 topics from the year, from the semester. Thermochemistry, all the stuff on heat and that stuff, with calorimetry. And then the other one is the one we're doing now, acid-base. So that's really what the final is going to be on, kind of more of the recent stuff. All the stuff on bonding and all that, we're not testing on the final this year. Thursday, right before finals, that double, I'll have tie-dye set up. So you guys will have to bring shirts if you want to tie, or whatever that's, tie-dyeable. It can be socks, I don't really care. And then I'll probably have it set up for ice cream that day as well, so you can kind of just have a mess around day. And then I want to take a class picture, kind of the tradition. And then that Friday, just kind of mop up. If you guys want to have a party review, it's up to you. And then we have finals. That's it. Then we say our second finals.
This is so sweet. I love this class.
You know where I work.
It's so
Okay, now.
fun.
Here is the last unit. Acids and bases and salts, oh my. So, I just want to show you some facts. I'm not going to ask you to memorize these facts, so if you want to look at them for a moment, it's fine. But then I want to zero in on really the heart of acid-base chemistry as we're going to study it. Kind of get to the facts, as it were, with a few demonstrations to boot. So, as far as acid-base chemistry, it's really about a tug of war between hydrogen, or between molecules for hydrogen ions. At least that's one definition that we're going to focus on. So it's all about hydrogen ions or protons being transferred between molecules. And that's really important in a lot of areas of chemistry and life. Whether we're talking about the food industry or just industry in general, cleaning, living organisms and systems, the environment, of course, and cosmetics. There's really almost nothing that I can think of that is not touched by acid-base chemistry in some form. Even if you're like a chef, acid-base chemistry plays a role. If you've ever used baking powder or baking soda, you've been doing acid-base chemistry. So the bottom line is, that's really what this is about. And it's kind of a fitting place to finish. Again, I'm not going to spend a lot of time on these slides. They're online. So you can go and look at these facts if you want. I'm not going to test you on simple recall mostly. It's going to be about process and application. So here is just a short list to kind of highlight my point that acids and bases are all around you. So these are common ones that you find around the home. Citric acid is that sour taste you get in fruits. Ascorbic acid is also known as vitamin C. We met that molecule when we did the molecular modeling lab a while back. Acetic acid is in vinegar. We're going to analyze a sample of vinegar as part of our lab this year, or this PM, to determine its acidity. Carbonic acid we find in soft drinks. We made some of that, remember, when I used the soda stream? Basically when we dissolve carbon dioxide. Lactic acid, you find it in milk, but you know where else you find it? Where? Your sore muscles, that's right. So when you have partially anaerobic respiration, your body cannot process glucose fully, and you end up with lactic acid. And the buildup of lactic acid in your muscles is that soreness feeling. And that's why sometimes kind of working out again a little bit after helps you feel better because you get that lactic acid worked out. Sulfuric acid is either the #1 or #2 from year to year industrially produced chemical in the world because it's used in so many different things. Place you see it around the house, your car battery. And that's why car batteries are dangerous. If you charge them the wrong way, they can explode. Like if you're jumping somebody's car and you do it wrong. If it explodes, you get sprayed with a really strong acid that can actually burn you pretty bad. And the hydrochloric acid, well, it's in your belly. It's part of how you digest your food, particularly like things like meats. That helps break them down. It's also why when you throw up, it kind of burns. It's the acidity. On the other side of the spectrum are bases. Detergents, soaps, things that we use as cleaning agents are often bases. Tums is an actual rock, effectively, that you eat. It's magnesium carbonate, sometimes calcium carbonate, and when you eat it, you kind of feel better after you burp because the reaction between the acidity in your stomach produces carbon dioxide. And that makes your burp and you kind of feel better when you have too much acidity in your stomach. Sodium hydroxide, otherwise known as lye. You probably don't have it lying around. But in the old days, that's how you made soap. And if you ask your grandparents if they're from the old country, they may have made their own soap. Maybe that's getting to be a dated thing, maybe you're great. Household ammonia, it's a cleaning agent again, but that's the one that smells really bad. Also basic.
Oh, that's smelling salts.
Yes, it is. And smelling salts, you produce the ammonia by, you break a packet and it mixes things and the ammonia comes off, wakes you up. And then baking soda, you probably have some sitting in your fridge right now, either for cooking or deodorizing your refrigerator. But again, this is a short list. These aren't the only acids and bases, but it's, just shows you they're kind of all around. All right, this again, I don't want to spend a lot of time on. I'm just showing you a quick list of properties, okay? So, one aspect, the word acid actually comes from the Latin word for acer, or sour. Things that taste sour typically are acids. That's how our taste buds respond to them. So you know those Sour Patch Kids? They have a huge amount of citric acid in it. It's not dangerous to you, but it gives you that sour sensation. This aspect, you've probably heard of litmus paper, but litmus is just a vegetable dye, and it changes color depending on the acidity. So in a acid, it looks kind of red, and in a base, it looks blue. But that was an early, what's called chemical indicator of acidity. And we have things like that now, but we have much more sophisticated ones. And I'll show you them as we demonstrate shortly. We've met this before. Acids are electrolytes. When you put them in the water, they make the water conduct electricity. And I think you remember a long time ago, I put a light bulb thing into water and tested different solutions, and the light bulb sometimes lit up bright, sometimes dim, and sometimes not. Reactive toward bases, because if you think about it, acids and bases are chemical opposites. When they react with each other, they neutralize, and they kind of knock out each other's chemical effects. But acids don't just attack bases, they can attack metals, and they can actually dissolve metals. We've seen that earlier in the year when we were working with, a long time ago, I forgot. We took manganese, or even magnesium, and we put it in hydrochloric acid, and it dissolved, and it generated hydrogen gas. And then they can react with a lot of things. So again, I don't want to get an exhaustive list here, but just to give you a sense of some of the properties. Bases, on the other hand, taste bitter. So like when you're tasting like black coffee, it's got some bitterness to it. There are certain compounds in it that are basic. Same with dark chocolate, it's more bitter, and that's why they mix sugar in it to make milk chocolate and make it sweeter. Bases, like soaps, feel slippery. So if you feel like slipperiness between your fingers, that's oftentimes something that has a basic property. They can, like we said, turn litmus back to blue. They are also electrolytes in water, and of course they neutralize their acid counterparts. So that's the essence of what acids and bases are like. Now I want to get right into the heart of acid-base chemistry. And the unit we just finished was on equilibrium. So I want to show you an equilibrium. If you take water and put it in a glass and just let it sit there at room temperature, the following happens. Can you look at what I wrote on the board and just describe to me what this is saying? Like, can you read that in plain old English?
H2O turns into hydrogen and, oh, hi. I don't know what that's called.
Hydroxide.
Yeah.
So this is hydrogen ion. And this one is hydroxide ion. And the early definitions of acid and base really are tied to water and things in water. And so I'm going to start there. But what I want you to look at when you see this is if you picture a water molecule, literally like this, like the old days when we drew the Lewis structures, you can imagine that if I pull this hydrogen off by itself, without its electron, it would look like this. And this bond is now just a lone pair here, and this is just the negative hydroxide ion. So literally, water molecules can split like this into two ions. So my next question is, why did I put a double arrow here? What does that mean again?
The reverse.
What?
Reverse reaction.
Yeah, it's reversible, which means this comes to some equilibrium, right? That's when we just have water sitting out, it's gonna get to a point and just stay that way. But my big question is, where do you think this equilibrium favors? Is it gonna be mostly just neutral water molecules, whole molecules of water? Or is it mostly gonna be broken into ions? What's your thought? Your instincts, what are they telling you? Maybe this would help. I happen to know the equilibrium constant for this equilibrium. If I write that, will you be able to tell me which way it favors? It's called Kw for water, and this is known as the water dissociation constant. And it has a value at room temperature that we're talking about, about 1 × 10 to the negative 14. So now, when I ask the question, is a glass of water mostly water molecules or mostly ions? How do you respond?
Water.
Yeah. This is almost all water, right? This equilibrium constant is stupid small. It's so small, it's almost hardly worth talking about. Because water is almost all water molecules, and very few of these ions are present. So why am I making such a big deal out of it? Because I think I can use this equilibrium to really take you straight into something you've heard of before, but maybe didn't understand why it is what it is. Let's see if I can do that. So let's do an equilibrium problem that kind of follows from where we left off in the last unit. So I take a glass of water, and I'm going to do one of those enough problems, because obviously what I mean by that is a glass of water is a lot of water. And we know that some of it, and let's pretend this is right before any of it's broken down. We know that some of it's going to break down, right? And every time one water molecule breaks, how many of each ion do I get from it? Well, in other words, look at the ratios. What do you say to that? I see we're going to gain one of each of these. And then when we get to equilibrium, when this stops breaking apart and basically comes to one constant value, right? This is going to be enough minus x, but who cares? It's going to be so small, it's ignorable. But we're going to end up with x of each of these. Now, if that's true, how do I write the equilibrium expression? For an equilibrium where there's a liquid, what do we do with the liquid again? Yeah, we basically ignore it. It just kind of falls out. So if I was writing this as an equilibrium problem, the expression would be the hydrogen concentration times the hydroxide concentration. And that would be it. There's no denominator, because this, as you said, is basically 1 for all practical purposes. It falls out. So here's our equilibrium expression. Let's solve it. We know the K, so that just goes in here. And we know it's x times x, which is x squared. And I think we can do this without a calculator, can't we? Yeah, you square root this. What's the square root of 10 to the minus 14?
10 to the minus 50.
Say again?
10 to the minus 50.
Disagree. Square root is like taking the 1/2 power.
10 to the negative 7.
10 to the minus 7. Yeah. Now, what X represents is the concentration of hydrogen, but it also represents the concentration of hydroxide, and they're equal to each other, aren't they, in pure water. So what we just found is the amount of the amount of concentration of hydrogen, which is the same as the concentration of hydroxide in that water. And as Joy points out, it's about 1 times 10 to the minus 7th molar. That's 1/10,000,000th of a mole per liter. Again, these numbers seem so stupidly small. It's like, why do we even bother to worry about it? However, I'm going to guess that either through junior high school or biology class in high school, you talked about something regarding acids and bases, about acidity. What am I thinking of that you might have talked about in biology related to acid base? A way to measure acidity, a scale, pH scale. And you might also have learned that pure water is an acid. So let me write this on the side. If I'm talking about pure water, so nothing's dissolved in it. Is it acidic? Is it basic? Or is it neutral? What do we know about pure water? Yeah.
It's acidic.
Disagree?
It's basic.
Disagree?
What? It's neutral.
You're getting there, yeah.
That's not taste.
What?
That's not taste.
It's not about the taste, but I see why you'd say that. It doesn't taste bitter, it doesn't taste sour, that's true. But for pure water, it's neutral. And I don't know if you know this, but does anybody remember anything on the pH scale at all, like what neutral is?
Alkaline?
Well, alkaline means basic.
Oh.
The value on the pH scale.
Was it 5?
Say again?
5?
No.
0.
No. So you don't remember, which is fine. That means you're learning something new, or remembering something. And when I write this, it might make sense with where I'm at. Yeah,
Is it 7?
it is. So let's write this down just to remind ourselves that when pH equals 7, solution is considered neutral in water. So what would acidic be? When the pH of it is, it's either above or below. You guys are really not good guessers.
pH below?
No way.
So 7 is kind of like the tipping point, but that just seems like such a random and weird number to call like neutral. Like, I get why you would guess 0, it just sounds like there's, nothing there, but I wonder why they came up with the number 7.
It's a nice daughter.
Because look at that's a 7 over there.
Whoa, look at this guy.
No, I didn't.
Wow.
Well, because I'm sure that equation has something to do with it.
Yeah, it can't just be a coincidence, can it? Like,
No.
why would I have gone down this whole path? Just so that would just be a weird coincidence.
No, it's probably because like when this is equal, that's a -7.
Okay, so now we're actually hitting upon, particularly an aqueous solution in water, what makes it acidic or basic. So, here is the key. A hydrogen ion concentration, this little guy here, is what makes an acid an acid. The hydroxide ion in water, in particular, this piece is what makes a base a base. And if that's all true, in pure water, where the water just kind of randomly splits the way we showed, what's always true in pure water about the amounts of these two?
They're equal.
And if they're equal, doesn't it make sense that it's balanced and it's neutral? Because either one's winning. So this condition, that these are equal, makes the solution neutral. And we can take a step further and suggest that that's the specific concentration of both of those ions in that water. It doesn't matter that that's the amount per se. Neutral just means they're equal. But in pure water, that's the amount that each of these is at. And it's, again, a stupidly small number. But now I have to go back to what Gabe said about
Yeah.
how do we get this scale of pH to be 7 when those are equal? Like, there's got to be some way to take a power of 10, pull it out of the number, and then turn it from negative to positive, right? I mean, isn't that kind of what we're doing if we're trying to turn that number into this number? How do you pull a number out of a power of 10 just to pull out the power? There's a math trick to this that you learned in algebra. What? Say it louder. You said it right. Say it. No one will be offended.
Log.
Boo! She said logarithms.
Stop it, you! You're bringing this into chemistry, please.
I didn't even know what was going on.
I'm taking geometry.
Why was it?
Wait, is this serious? You're actually serious?
I was joking.
In our class, though, all you have to be able to do, now hear me out, is push the button that says LOG on the
I
calculator.
don't have a calculator.
Whoa,
If you can do that, you're going to
I don't think it can. Wow.
I don't know, I didn't even know yet. Why are we mixing algebra?
be. Ladies and gentlemen, in TV land,
This is confusing.
I implore you, forgive them, for they know not what they say. All right. So let me just show you the connection between what you just discovered and what we've been talking about. The connection is right here. We can define the pH scale as follows. And I'm going to move this out of my way because we don't need this part anymore. Here is the definition of the pH scale. And then you'll see how hopefully all the pieces connect. And then I'm going to relate all the different possible equations you need to work through these problems. So, and it may be, and I don't have historical confirmation of this, that the reason why it's called pH is that P might stand for power, as in power of hydrogen. I don't know if that's true. I've read that in some articles, but nobody has a definitive answer to why it's called pH. But P is a function. Just like when you see this in math, it tells you to multiply, right? When you see this in math, it tells you to divide. When you see this in math, it tells you to take the logarithm. So functions in math have symbols to represent them. And P is also a function. When you see P something, it's telling you to take the negative log. And so all pH is saying is if you take the negative log of the concentration of hydrogen ion, you're finding some number. And in our case, if we go back to the concentration of hydrogen in pure water, you'd be taking effectively the negative log of 10 to the minus 7. And remember, when you just write log, it's base 10, right? Because we're only going to use base 10 for this. We don't need any other logs to work with. But doesn't log and 10 just undo each other?
Yeah.
Like 10 to the power? So isn't this going to come out as a negative 7 if we took the log? But the negative sign in front is put there to get rid of the other negative sign, because people like positive numbers better. And so when you do this, you get a pH of 7. So let's connect the dots here. When I take pure water at 25 degrees Celsius and just let it come to equilibrium with the ions it can break into, I get an equal concentration of both ions. That means that the acid and the base components are equal. That means the solution is neutral. And by our equilibrium calculation, we found those concentrations. We now define a new scale called the pH scale that allows us to turn in this weird-looking power of 10 into a simple number. And that's the reason why it's done this way. Now, let's see if it makes sense according to how things should move on this scale. Does anybody happen to know what the range of the pH scale is typically stated as? Like how much it goes between?
0 and 14.
It's pretty close. I mean, that's right, that's usually where people put it. So if you take the pH scale and set it to 0, put 7 in the middle, and then 14 on the other end. Let's see what this all means. So we've already identified that here it's neutral. Okay. What happens as we start moving towards 0?
Becomes more basic.
Now,
More acidic.
That's correct. pH is kind of like golf, the lower score is better. But really, let me explain why this happens, because it is kind of, it sounds like it's backwards, right? So as we're going in this direction, two things are happening. The concentration of hydrogen ion is going up. We're getting more and more hydrogen. And the concentration of hydroxide ion is going down. But for the pH scale, we only care about this fact. But wait a minute. Why would having more hydrogen make the pH go down? Let's test that. Oh, Casey, go ahead.
Yeah, because taking the negative log of a number of like 10 to the minus 6 is smaller than, or bigger than 10 to the minus 7.
So that's very good. That's very good. So if I had changed this number to -6, just to make the math easy in our heads, isn't 10 to the minus 6 a bigger amount than 10 to the minus 7? Right? It's a larger value. But when you take the negative log of that, the pH goes down. Meaning that the lower the pH, the more acidic the solution. The lower the pH, the more acidic the solution. Which means there's simply more hydrogen ion in the water. But wait, you might be asking me. You just said when water breaks apart, the H and the OH are always equal. Why is there ever a solution that has a pH less than 7? It doesn't make sense. Unless, what? That's possible. And there's a couple ways we can do that, but here's my problem. Even if I shifted this equilibrium toward the right and just used water, wouldn't these always be equal? Could be more of both, but they'd be equal. I wonder if there's a way to get more hydrogen into water. Can you think of anything we might be able to put in water that would increase how much hydrogen ions are in it?
Hydrogen.
Good. From where?
Hydrogen.
What? There's not much hydrogen in the air, and that's a good thing. Because if there was hydrogen in the air mixed with oxygen, the first person who discovered fire would have been the last person. Because he would have blown up the atmosphere. That's bad. Can you think of something that we could put, and this goes way back to first semester when we did naming, and I think we did some naming of acids. And at the time we didn't understand their function, but we understood what they looked like. What? Anyone? What about something like this? What would happen if I was to take HCl and put it into the water? What might happen?
Everything explodes.
That could happen, but it won't. Well, let me ask you this. Is it possible that this can break into hydrogen and chloride?
It's very plausible.
So couldn't this be a source of hydrogen in the water?
Yeah.
And this would put more hydrogen in, but not more hydroxide. And in the end, we'd get a surplus of H plus in the water, and it would become acidic. The pH would drop. Let's try it. Let's see if this is true. So it turns out I have just those things here to show you. I have a couple ways to show it to you.
Exactly.
Can y'all see this number up here?
It says 1.4.
Yeah.
All right, so what I have right now plugged into the computer is a pH meter. So this actually lets me measure
Say
pH.
it like that.
And, you know, these are a little tricky, they're not perfect. The temperature matters and such, so we're gonna see, I think, reasonably close to what we expect. So let me start by grabbing just some straight up water out of the sink. You might say, well, why don't you use the DI water? Well, interestingly, DI water tends to dissolve carbon dioxide, and that changes its pH. So I'm gonna just grab some tap water, and I'm gonna show you what I can do. So you watch the number.
I know the problem.
All right,
Let me show you what
now,
I can do.
you guys, if you're not listening, you can't hear me. So if I was to take this pH meter and now place it in the water, this is just essentially pure water, what should the pH read from what we've been saying?
It's neutral. 7.
It should be about 7, right? So it takes a moment to respond. I just have to kind of shake off any chemicals that were on the bulb from before. I'm gonna lay that there for a moment while I get the next thing to add. Okay? Now,
We have to.
while our meter is doing its
I have
thing,
it. We don't. We don't. So many words. Like everything is connected somehow.
Just mix random chemicals together.
Sometimes people get a 5.
thank you. So while that's happening, I'm gonna take something you may or may not have played with before called pH paper. And if you look,
I still have that.
if you look on,
That's a good
if you look on my face and I'm going, you'll notice that there's a color scale that kind of matches pH best, you know, within like approximate at least, that you can match it to the color. But if I take this and dip it into the same water,
Nothing happens because it's neutral.
you'll notice that it's pretty close and it's hard to see because it's somewhere between 6 and 7. And again, that's fine because this is probably, again, there's some stuff in the water from the tap, but it's pretty close to kind of hitting that greenish color, which puts the pH at around 7. And again, this isn't quite to the end there, but it's getting close. But we're pretty close to a pH of 7. Yeah, it's a little bit. So here's the thing. What I want to show you now is I have some hydrochloric acid here. And I'm just going to dribble a little bit in. And like we said, in theory, the chlorine really shouldn't do much. But the hydrogen that this provides, the hydrogen ions, should do what to the pH?
Lower it.
Let's see if that's right. So I'm just going to squirt some in there.
Oh, it's so much.
And I'll just put a few drops at a time.
It's right here.
And the pH is going down, right?
Yeah, here always looks like that.
That instrument is designed to detect and measure
Are you excited?
the concentration of hydrogen
They're
ions
very big.
and then report it as a pH. In other words, it's designed to not only find the hydrogen concentration, but then basically take the negative log for us and report it. Now, my claim is that, yeah, I just measured the pH. And it dropped because I added in a source of hydrogen. But I think, without knowing even what I threw in there, there's a way that we can now take that pH value and figure out the concentration of hydrogen in the water.
Well, it's an equation.
It is, but the equation's already on the board. You just don't realize maybe how to flip it around, unless you're casing it.
Is it not 10 to the negative 3.3?
Right.
Whatever it is, right?
That's what I was gonna say.
Good. That's right.
No, I don't wanna sound like a Casey, like poser, but I was gonna say that.
That's good. So let me show you.
I mean, I even gave you the lead up there.
Let me show you next to this equation how we could basically invert it and turn it into the concentration of hydrogen. So let's say I wanted to turn this equation around and solve for the hydrogen ion. The first thing I would do is move the negative sign over, basically multiply both sides by -1. And if I did that, I then have to get rid of the logarithm. And since it's base 10, I would just do this. I would take 10 to the power on both sides. So ultimately, let me go back to where this was. The two equations that are kind of inverses of each other, this is if I know hydrogen and I want to find pH. But if I know the pH and I want to find the hydrogen concentration, I would just do that. So these two equations are the same equation, just inverted, okay, inversed. So actually, by using the pH, I know it's bobbling up and down, but let's just take the value at 3.73 and let's do the concentration calculation. Now, you can write this, but you can't leave it this way. Okay, that's not like a meaningful number. So what I would say is, in our calculator, and this is again the extent to which the logarithm skill you need is just to plug the numbers into the calculator. But if I take the pH that I just recorded, which was 10 to the negative 3.73, I could literally just use the caret system, 10 to the caret and whatever. Or if you look at the log button, I'll pull this down. If you look at the log button on the calculator, the second function is 10 to the x. That's just the inverse log. So I'm going to take the inverse log of negative 3.73, and then the calculator does the rest. So according to the calculation that I just did, I added enough acid, according to my measurements, such that the concentration of hydrogen ion is now increased to about 1.9 times 10 to the minus 4th molar. Now it starts to make sense why the pH scale works the way it does. Why did they use logarithms? Because the range of possibilities is ginormous. You can get all the way from essentially 10 molar, or 1 molar, to 10 to the minus 14th molar at the other end. It's such a wide range of powers of 10, a logarithmic scale makes sense, so that it can be condensed into like a 0 through 14. Okay, now just to kind of corroborate this, let me take another little bit of pH paper and dip it in here. And if we're right, what color should we see if it's around a pH of a little less than 4? Can you see if
No one can read that.
it's somewhere in the kind of reddish orange
Reddish orange.
range. So if we dip it, you can see that effectively it's somewhere around 4, just like we read. Okay? Now, everything I just argued and everything I just said, we could do as well from the other side. In other words, what if I wanted to go the other way and make the scale go that way toward 14? What would be different?
It's the opposite. You just take the hydrogen down.
Yeah, the hydrogen would be going down,
So add a
but the hydroxide would be going up. And can you think of something we could add to water that would increase the amount of hydroxide in the water? Yeah,
hydroxide.
yeah, and there's a lot of different metal hydroxides that we could use. The classic example would be something like sodium hydroxide, NaOH. When you put this in water, the sodium part comes off and the hydroxide part comes off. And again, this piece and this piece are irrelevant. It's the fact that we've added more hydroxide directly that makes the water more basic. Now, interestingly, it turns out that we can take and create another scale. We can say, well, there's a POH scale too. No one ever really does much with that, but just to make the parallel argument, doesn't it make sense that that would just be the negative log of whatever the hydroxide concentration is?
Makes sense.
And inversely, wouldn't it also mean that the hydroxide concentration would be 10 to the minus PO8? So what do you think I'm going to do next to kind of verify this?
You put in more NaOH and test in the thing.
Yeah, so I'm going to actually keep my same solution that if we're reading the pH of right now, is still acidic. Because I want to prove something at the same time. Don't worry, I'll move the screen up and down. So I happen to have some sodium hydroxide solution. I could have do it with a solid, but here I have it in solution already. What I want to do is I want to push it to go basic. How's that going to work? It's already acidic. Can I push it back the other way? If I'm really careful and only add just the right hydroxide, could I bring this back to 7?
You gotta be precise.
And if I go past 7, that means I put more of this than the hydrogen, right? Let's see. So I'm going to do that now. I'll try to go slow first.
Super quick. You know what we're doing.
Is that recording?
See, already it's going up dramatically because the base I added is neutralizing the excess acid. Who's still winning? Hydrogen is still higher than the hydroxide. Let me go overboard now. I think that should be more than
Oh,
enough.
what?
That's
Crazy.
What? The question is, this is a good question, and I'm going to ask it both ways, but let me put on the board so you can see. Is it possible that the pH scale can go below 0 and above 14? Is it possible? Is it possible? What do you think?
Yes, but it would be extreme amounts, because negative 14 and 4 to the 14th and the negative 14% tiny amounts.
Right, so for this to get negative, the way logarithms work, to get to 0, you take the log of 1. So once your log gets bigger than 1, the output is going to be negative. So like if you had a 10 molar solution of hydrochloric acid, this would go down to -1. So the pH scale can go negative. And if you had a sodium hydroxide that was, let's say, 1 molar, or 10 molar, I should say, you would then go past, you get up to 50. So absolutely, you can. But those are, like you said, the extreme high concentrations. Now, let's see if we can make sense of this, because we got to be really careful now. Because remember, my instrument only measures the pH. So how do we get and prove the hydroxide if we're only given the pH? So if I know the pH is 11.76, we already know this solution is basic, right? Because on this side, it's becoming basic. But how do we get the numbers? Like, can I figure out all the concentrations of hydrogen and hydroxide just from the pH? Well, there's a couple things we can do. You see these kind of 4 equations? They're part of a set of 6, and I'm going to show you the other 2 right now. It turns out that the pH, and I'll summarize them again at the end. The pH added to the POH always equals 14. And that comes from the fact that the product of the hydrogen and hydroxide concentrations is equal to 10 to the minus 14. This is just the logarithm form of this. These are really the same equation. One's in just normal form, and one is in, well, I should say exponential form, and one is in logarithm form. These are really the same equation, and we can prove that with the rules of logarithms, but based on your first look when I said log, and everyone's like, ooh, I think we'll just leave it at that. But there's a couple ways we can operate this. I can take the hydrogen concentration out of this and then use it to find the hydroxide. Or I could find the POH first, because what would I do if I know the pH? and I want to find the pOH. Yeah, you just take 14 minus that. 12, 13, 4. Is that okay? So now I know what the pOH would be. And just like this shows, I can calculate the hydroxide concentration as 10 to the minus 2.24. And if that's right, wrong button. 10 raised to the minus 2.24. So I get a concentration of hydroxide of about, I'll call that 5.8 times 10 to the minus 3rd molar. So that's a pretty, starting to get like a pretty high concentration because I dumped a bunch of hydroxide in there. And then if I wanted the hydrogen ion concentration, from there, I have two choices. I can just do the pH, 10 to the minus pH, and get that. Or I can do, from this equation, if I know one of these, and I know this constant is always the same, I can just divide. So the hydrogen I could find by doing 1 times 10 to the minus 14th over the hydroxide. Or I could just do 10 to the minus pH, which here is 10 to the minus 11.76. If you do either of these within rounding, you're going to get the same answer. Because again, the essence of this is that as hydrogen goes up, hydroxide must come down, since their product stays constant in water. And in this case, if we actually do the math, it would be 1 times 10 to the negative 14. Oops, negative 14. Divided by the number I just had. So I'll just take it from my previous answer. Or about 1.7 times 10 to the negative 12. So there's the molarity of hydrogen in this solution. There's the molarity of hydroxide in this solution. And we can see that the hydroxide is bigger than the hydrogen, and therefore the solution is basic. And that's why the pH is greater than 7. So that defines the pH scale. Before I go on, I want to do a quick demonstration that I think you'll find amusing. So you might wonder, how do they make a piece of paper? Oh, we should test that too later. So if the pH is basic and around 11, can you see what color it should be about? Where 11 is? Kind of a bluish color. So let's see if that's right. So there's the pH color. It's somewhere between 10 and 11, I think, pretty fairly. How do they make a paper that has all these different colors that respond to the pH? Yeah.
Does it react to, do you have like something that reacts to acidity?
Yeah, but there's not one molecule that has this whole range. So what they do is they have a mixture of different indicators. And depending on the pH, how much hydrogen and hydroxide are present, it's going to affect them and change the color in the regular way. Let me show you what that looks like on a bigger scale. This solution is called universal indicator. It's a mixture of molecules that, depending on the pH, change their form and what color of light they absorb. So I'm going to make a solution of this from water first. That's about enough. And since this is just plain old water, this should show us kind of that greenish color. This is the part that's a little risky because I tend to spill this a lot. All right, let's see if I make a mess. So I'm going to pour it into this tube. Hopefully you can see the color a little better this way. I'm going to leave myself just a little bit of space. This is the part where, like I said, I tend to make a mess. So now I'm going to come back here and get my acid solution and my base solution. You're all just waiting, like kind of watching a car race. You're just waiting for it to fall on me and spill, aren't you? That's the best
Why
part.
do you put the glass different?
It's lavender purple too.
Can't remember which is which now, which is kind of the same. That's the base one.
I need a crocodile.
All right, so I'm going to take a little bit of the acid solution, a little about a squirt, and pour it in this side. You can kind of see the redness.
Wow, he's really good.
Now I'm going to close this end and try not to spill it all over myself. And on this side, I'll wait for the air bubble to come back. But just a little bit, about the same amount of base on this side. Because if I'm really good at what I do, and don't spill it, and let this kind of mix a bit, we create a rainbow tube. We can show the entire spectrum of pH here, from purple, which is 14, down to red, which is about 1. And the reason this is happening is we're creating a hydrogen hydroxide concentration gradient. Probably needs a little more acid.
I'm not seeing too much red, Jake.
Yeah, we'll help you.
Thank you.
All right.
Wow, okay, that's
Better?
better. Now switch to this side.
Give it a quick mix. So our rainbow tube basically shows that at one end there's a much higher concentration of hydrogen ion, and at the other end there's a much higher concentration of hydroxide, and in the middle it's about equal, right? Where it's green? I'm pointing with my nose because I ran out of hairs. Yeah.
What happens, will it ever fully mix?
If I leave it long enough and it fully mixes, and I put equal amounts of extra hydrogen and hydroxide, what should it all eventually become?
Become the same thing?
It'll go back to green again.
Oh,
And if I had too much of one or the other, it will go to one final color that's going to indicate whether I put more acid or more base.
so at the current, if you just leave it for a bit, it'll balance out eventually?
Eventually it will. But right now I'm just helping it mix by turning it back and forth. And I'm just trying to see if I can get it back to green. But ultimately, it's just to show you that the pH scale is really a way of measuring the hydrogen and or well, really the hydrogen, but then indirectly the hydroxide concentration. And that acid-base chemistry is largely based on that. But another question comes up. Yes? Yes. What kind of compounds? We saw only example one of each. What kind of compounds do this? What kind of compounds make acid-base solutions in water? So if we can generalize that, I can also explain to you the different ways to look at acid-base theory. So the first definition you need to know is called the Arrhenius definition. It's the older one, and it's the one I've been focusing on up until now. So pretty much, if I want to be an acid, I basically have to have hydrogen ions that I can throw into the water. So anything that has hydrogen, and do you remember when we did nomenclature?
No.
A long time ago, at least you might remember, I said if it's an acid, it starts with H. And the reason I said that is because those H's were ions that these molecules could give up. And when they give them up in water, the water becomes more acidic. So in general, what Arrhenius came up with, Svante Arrhenius said, look, if I put something in water and the hydrogen ion concentration increases, that's an acid, because it puts the H pluses in the water. On the other hand, if I take something and the OH, hydroxide concentration goes up, then that's a base, because it makes the hydroxide concentration in water go up. And you can see here's a few examples of compounds that have that hydroxide that could be broken off as an ion. And if you take one solution that has extra hydrogen and another solution that takes extra hydroxide or has extra hydroxide, and you mix them, they react and form water and neutralize each other. And water seems to be at the center of acid-base chemistry. However, not all chemistry happens in water. Is there a more general way to view what's really going on here? Because this is the way most people first-year chemistry learn acid-base. the way we just described. But there's a lot of more interesting ways that you can look at this. For example, if you take something called ammonia, and you may remember I did a demonstration like this a long time ago. I took ammonia and it was very concentrated and I put it under the fish tank. And then I put HCl also under the fish tank. And then do you remember it made it look like a smoke cloud inside? It looked like a mushroom cloud.
Did we do?
No, I don't remember that.
We did it because I did it during gases and we talked about diffusion and the rate of diffusion. And I asked you guys, why is the smoke cloud forming closer to this one? And you told me, well, it has the higher molar mass, so its molecules move slower. You did it.
I don't think we did that.
I don't think we did.
What
that.
fish
Listen,
tank?
I don't know why you guys want to go swimming in Egypt right now.
It was anything special.
You're in denial.
It's like a
Okay,
box, like a clear box.
anyway, it turns out that if we look at the Lewis structure of ammonia and the Lewis structure of HCl, what was happening in that reaction were gas phase molecules were interacting. But look at what's happening. Ultimately, hydrogen was directly transferred to ammonia, and it formed something called ammonium chloride. And that's the smoke we saw. So it formed this ionic compound. But what's more important is two facts. This doesn't seem to fit our current definition of acid-base chemistry because there's no water involved. And I don't see any OH. So what's going on here? It turns out there's a more general understanding of how an acid-base reaction can work. And it has to do with the transfer of that hydrogen ion. So, while the Arrhenius definition is quite useful, it's kind of oversimplistic and doesn't really capture the true nature of the reaction of acids and bases.
Yep.
So a broader definition comes to us from the Bronsted-Lowry model. This model treats any molecule that can donate a hydrogen ion as an acid. By donate, I mean lose it to something else. And it treats a base as any molecule that can accept a hydrogen ion. So instead of focusing only on things that happen in water, this generalizes acid-base chemistry to a much broader spectrum of things, and it actually makes more sense because what this is saying is true in water too. This is just a more general way of looking at what's going on in water. But otherwise, this definition covers the Arrhenius and then some. So, to be an acid, I still need that hydrogen to give. But to be a base, all I need is a lone pair of electrons to attach the hydrogen ion. So anything with a lone pair of electrons can technically act as a base. There's a place to put a hydrogen ion on it. And this is the definition we're going to operate from. And so, really the last thing I have to explain to you is the concept of conjugate acids and bases. And then I'm going to turn you loose on the assignment. In case this seems like a lot and it's overwhelming, that's okay. I've been trying to go at a pretty reasonable pace, but I know it's a lot in one day. But it will be on video, so you can watch it back later. And, you know, kind of pause or slow down or review parts that weren't clear when you're doing the assignments. So let me just finish this last bit, and then I'll let you kind of practice or decongest your brain, whatever you need to do. But I remind you, of the 2 assignments that I've posted, I will pick a couple from each. Like I'm saying, 3 to 4 total questions based on today's lesson. And I'll bring it tomorrow for you to take the quiz on. Let's just see where you're at. You don't have to turn in the homework. You don't have to do the homework if you don't want to. But I'll let you use the assignment that you do on the homework quiz. So if you want to get 100 on the quiz for sure, all you have to do is every problem 100% correct. Or if you're somebody who's like, you know what, I'm just going to look at a couple. If I get it, I'm done. I'm not going to write it down. That's fine. You can do that too. All you have to show me is that you get it. Don't have to do anything else. All right? So let me show you what I mean by conjugates. Let's look at a little more carefully the reaction I put on the board a moment ago. This one. But I'm going to put it in water again, just to kind of make my point. So let's say, for example, that I take some ammonia and I put it in water. I find that it reacts to form ammonium ion and hydroxide ion. If we look at the definition of acid and base that we just finished describing, the one with Bronsted-Lowry, I'm going to tell you that there are 2 acids and 2 bases in that reaction equation. Can you identify who the acids and who the bases are, and how could there possibly be 2 of each? By the definition I just said. Even if you just name one or another, I just
An acid is NH4 an acid.
You're calling this an acid?
Yeah.
I agree. Casey, what do you see?
NH3 is also an acid.
Can't be. It has hydrogen, right? So you're thinking that way. But in this reaction, look at what the reaction is saying. Look at the movement of hydrogen ion.
Because it released.
Did it? This
No,
released?
it gained
Where did it gain from?
H2O.
So isn't this forming because hydrogen went from this one to this one? Specifically hydrogen ion?
So that has
You
to
see
be
how
base.
this makes these products?
So that's the base.
So this is our donor, right? This is our acceptor. According to Bronsted-Lowry, whoever gave up the hydrogen is the acid. And whoever accepted it is the base. What? I thought water was neutral, now it's an acid?
That's great.
Hold on, it gets better. Where's the last base?
The base is OH -1.
Now, what I want you to notice is that the forward reaction, the hydrogen moves this way.
Oh, that makes sense.
But what's happening if we do the reaction backwards? Which way is the hydrogen moving?
The hydrogen goes back to OH, which makes it the base because you're giving the donor is the NH +4 +1, and then the acceptor is the OH -1.
Right. And what I want you to notice from this is that the acid-base pairs are related. In other words, if I connect these two, you can see they came from the same structure, right? One is the acid form, one is the base form. And then if I look at the water and the hydroxide, those are also related. One is the acid and one is the base. When they're connected like that, when they're related that way, they are called conjugates of each other. That's just a fancy word for related. And we can now generalize this idea. But let's do one more example before we generalize. So I'm going to take another acid, and I'm going to mix it with water again. And really, what I really want to hit home here is acid-base definition is a behavior. Just looking at the structure isn't enough. You have to see how it's reacting. And I'm going to put this in water again. And if I told you the products were these, and this is going to look weird at first, but I'm going to explain why. Just from the behavior and the movement of hydrogen ions, who's the acids and who's the bases in this second example? Who's the acid, who's the base? Hey, do you know what? In this case. You're calling this a base? Where did it get the hydrogen from? From this guy, right? So So if he's giving the hydrogen here, what must this one be?
Acid.
Now, if I asked you, if this is the acid, what's its conjugate base? Which is the base form of this? And you can answer that by looking on the other side.
C2H3O2.
Right. This happens to be the base form of this, because we've lost the hydrogen and formed this guy. So this now becomes the base, or specifically the conjugate base of this acid, the related base. And then what must this be? Because if we ran the reaction backwards, the hydrogen would move in this direction. Donor, acceptor. Donor, acceptor. Oh, wait a minute, now water's a base? So what I really want you to understand is from this point of view, nothing is an absolute acid or base in itself. It's in the behavior. Some molecules are able to act as acids or bases like water does. What's so special about water when we look at its structure that lets it do both behaviors?
Because it has, it can make OH and it can make hydrogen.
Yeah, it has both things. It has hydrogen that something can steal, right? It's got hydrogen it can give up. But it also has a lone pair where a hydrogen can be seated. It has the ability to do both. There's a fancy name for that. I don't care that we know it right now. But I do want to name this thing. This is called hydronium, and it just sounds cool. What did you learn about in chemistry? Hydronium. And you have to do it with an English accent. There's no other way. Hydronium. It sounds so sciencey. But hydronium is really kind of the more common way that we think of hydrogen ion. In other words,
Spicy water.
for all practical intents and purposes, this is basically the same thing as just saying this. But in some ways, this makes more sense. Because if you have a solution that's mostly water, and then all of a sudden these free hydrogen ions are rolling around, doesn't it make sense they're just going to kind of stick to a lone pair when they find them? And so we find that hydronium is just another way of representing hydrogen ion in water. But I just thought that this introduction, I know it was long-winded, would kind of give you the big picture from which now you can kind of hack away at the kind of questions that I'm going to ask you. So your assignment to study from, just so you can get a sense of it, looks like this. And again, I know this might have been hard to stay with the whole time, and I appreciate you trying. But if we go back and look at the assignment, the first problem set is mostly asking about the definitions, conjugate acid-base pairs. So just to get you started, this question says, give the conjugate base. All you do is rip off H+, and what's left is the base. In other words, if I give you HCl, and I say that's an acid, if I want to know its conjugate base, just take away one of its hydrogens. That's the conjugate base of this acid. If I gave you the conjugate base NO3-, how would I know what its conjugate acid is? Just put the hydrogen plus back on. What would this look like if I added H+ to it? So if I'm going this way, I take away the H+, and I figure out what it becomes. That's the base form. And if I'm going this way, I add the H+ back on to see the acid form. And that's really all this first part of the assignment is about. And a little bit of math. And then the second part is going to have problems of calculations with the pH scale that we talked about. All right. So this homework is where you're going to work out your issues with the lesson. I leave it to you now. If you want to just rest, leave it to you to do that. If you want to study, study.